In this video, we're going to be working through the solutions to some practice problems involving electric potential energy and voltage, specifically focusing on the relationship between electric potential energy and voltage and the use of electric potential energy using the conservation of energy. Now, before we get started, we'll just go through the basics that we need to know in order to solve these problems. So first of all, we had an equation that we wrote down, which is that the electric potential energy is equal to the charge in a voltage, right, times the voltage at that particular point. Now, one way that we can write this as well is saying that the change to the electric potential energy is equal to that charge's value times the change in the voltage, right? And then we're going to use this equation, or one of these equations, in the conservation of energy. And usually that's looking at the interaction between the electric potential energy and the kinetic energy. And so what we had previously seen is that the expanded but general form for the conservation of energy with these problems is saying that there's a kinetic and an electric potential energy in the initial state and a kinetic and an electric potential in the final state. So we can write that out like so. We're calling us all the way back to our unit on energy. We can write the equation for the kinetic energy. Alright, so with these basic equations and relationships in mind, let's start looking at these problems. Alright, so for this first problem, I've got a 15 nanocoulomb charged particle moving from point A, where the electric field is 300 volts, to point B, where the electric potential is 300 volts, to point B, where the electric potential is 200 volts. So let's get started with just writing down a diagram for the situation. So I've got a positive 15 nanocoulomb charge, so let's just give that the sign Q, and it's moving from point A to a point B. Right, so this is my initial state, and this is my final state. Alright, so Q is equal to 15 nanocoulombs. And then I can have my initial and final voltages as well. And so the first part of this question is saying by how much does the electric potential change? So again, there's a linguistic trick that's happening here, or it can be tricky or trip you up, which is that when we're talking about electric potential, I could say electric potential, I could say potential, I could say voltage. They're all talking about the same thing, but they are very different, well, definitely different than the electric potential energy. So we really need to be paying attention to the fact that this question is asking me for the electric potential and not the electric potential energy. So for this first part, all it's asking me for is the change to the potential or the voltage in this situation. Now, anytime I'm looking for a change, that means I'm doing the final minus the initial, so the final voltage minus the initial voltage. And so in this case, that means that I'm doing a negative 200 volts minus a 300 volts for a final answer of 500 volts. All right, for part B, says by how much does the particle's electric potential energy change? So now we're looking for the change to the electric potential energy. And in our review of these equations, we said the electric potential energy, the change to the electric potential energy, is equal to the charge times the change in the voltage or electric potential. And so we found the change to the electric potential in the last part, the negative 500 volts. And so I can find the value by taking my 15 nanocoulombs times my negative 500 volts. Right, and that is going to give me a value of negative 7.5 times 10 to the negative 6 joules. Right, joules being the unit for energy. And then last, it's asking for how my answers would differ if the particle's charge were a negative 15 nanocoulombs. Now, we can just go through this with the equations, right? For part A, I'm saying that this is the change in voltage. voltage final minus voltage initial, well, that doesn't involve the charge at all, so that's telling me that the voltage, the change in voltage, is still going to be negative 500 volts. But then for the second calculation, if I now have a Q which is negative, then I'm going to get the same magnitude but the opposite sign for my change to my potential energy, my electric potential energy. So that means that the change to the electric potential energy will be a positive 7.5 times 10 to the minus 6 joules. The other way that we can think about this first part, the unchanged voltage or the change in electric potential, is that the electric potential at each of these points A and B is determined by some sort of source charge that we don't have a lot of detail about in this problem. We just know that at point A it's 300 volts and at point B it's negative 200 volts. But that's determined by some other charge that's not my 15 nanocoulomb charge. And so we know that that voltage isn't going to be changing, right? The only thing that can change at this point is the electric potential energy, right? The reaction to that voltage, right? And so this is going to be important when we're looking at the second question. We're saying by moving a 10 nanocoulomb charge from point A to point B, you determine that the electric potential at B is 150 volts. What would the potential at B be if a 20 nanocoulomb charge were moved from point A to point B? Right? So we know that the voltage at B is going to be equal to 150 volts. Right? So there's some point in space, B, that has this voltage of 150 volts. Now that voltage is being determined by some source charges that are in the area. Again, we don't know exactly how this voltage is being created, we just know that there's this point somewhere in space and it's got this value of 150 volts. Now, if I have a charge in that voltage, right, that will create an electric potential energy for that charge, right? But that charge in the voltage, right, will not be affecting the voltage itself, right? Someone else has laid down the groundwork, right, has set the map, and now we are just reacting to the hills and valleys that have been created in it. So by changing the charge from a 10 nanocoulomb to a 20 nanocoulomb charge, I'm going to double the amount of electric potential energy that that charge has, but the potential will be unchanged. The voltage at that point will be unchanged. All right, so for my answer, the voltage at B is still going to be 150 volts. It doesn't matter what charge I put there, that's still going to be the value for the voltage unless I start manipulating the charges that are creating the voltage in the first place. Right, and then last we're looking at this conservation of energy. So we've got a proton that moves through an electric potential created by a number of source charges. Again, we really don't care about what those source charges are, how they're made, right? Because it tells us that the potential at a point is 1500 volts, right? A point where the proton is moving at 2.5 times 10 to the 5th meters per second. And so we're looking for the proton speed a short time later when it reaches a point where the potential is negative 500 volts. So I'm going to start by taking a second and just writing down the things that I know. Alright, so I've got the initial speed, the initial voltage, the final voltage, and then the things that we know but we are not given, right? The charge on a proton is 1.6 times 10 to the minus 19, and then the mass of the proton, 1.67 times 10 to the minus 27 kilograms. Alright, so we're looking for the speed sometime later, right? My final speed. And so we're using the conservation of energy. Right, before we get started, we should write down our system. Right, by including the proton and the source charges, I've made sure that all of the forces on my proton are going to be internal to the system so that my system is isolated. So that I can use the conservation of energy, which is going to say that the change in the total energy is equal to 0. All right, so I'm going to work through this again. to see how we got to that general form that we put in the review. Right, the change in the total energy being 0 means that the initial total energy is equal to the final total energy. And so we're asking ourselves, what forms of energy do we have in the initial state? What form or forms of energy do we have in the final state? So in the initial state, we know that we've got some kinetic energy because we've got an initial speed. We know that we've got a electric potential energy because we've got that initial voltage. In the final state, I'm solving for my final speed, so I know that I've got a final kinetic energy and I've got a final electric potential, and so I can add in that term as well for the electric potential energy. All right, so we're looking for the final speed, which is going to be in my kinetic energy finally. So let's start expanding this out. All right, now we can just go through at this point and just check everything off. All right, we've got the mass of a proton, we've got the initial speed, we've got the charge, we've got the initial voltage, mass again. We don't have the final speed, but that's what we're looking for. Right, we've got the charge and we've got the final voltage. All right, so the only thing that I don't know in this equation is my final speed, and so I can solve for that algebraically. All right, so I've got my final expression for the speed, right, the square root, the mass of the proton times the speed initially of that proton squared plus 2 times the charge of the proton, all multiplied by the quantity, the initial potential minus the final potential divided by the mass of the proton. And when I plug in my given values, I got a final answer of 6.7 times 10 to the 5th meters per second. All right, so as I'm going from a higher voltage to a lower voltage with a proton, a positive charge, I'm seeing that the speed of my proton, my charge, is increasing. All right, so that's it for this video, working through those problems. If you have any questions, let me know. Otherwise, good luck out there.